Okay, next section, 2.5, I think, implicit differentiation. Right. So first of all, what do these words mean? Differentiation, right, that's a long word, but it just means the process of taking the derivative. Right. So it means taking the derivative. Right. And some books will actually use that word. Instead of saying find the derivative, right, of, f of x equals x to the fourth, it'll say differentiate the function x to the fourth, right? And either way, your answer should be the same, right? 4x cubed. Right. Okay, so yeah, differentiation means taking the derivative. So implicit means that we're doing it implicitly. So I guess the best way to contrast that is what we've been doing. So far, everything we've been doing is explicit differentiation. In other words, we have a function, right, either y equals x to the fourth or f of x equals x to the fourth, and we explicitly take the derivative. Okay. So in this section we're going to be doing implicit differentiation, which is much the same way, but it's in the context of looking at equations rather than functions. Okay. And so before we go any further, I really want to emphasize this point here, that when you have a function, let's say a function of x, right, and you want to take the derivative, we usually write it as f prime of x. Right? So in other words, y is the dependent variable, x is the independent variable. Right? And we can also write this as dy over dx. Okay? Right. So what happens if we have, say, y as a function of t? Could be sine of t. Well then, if I take the derivative, this is the derivative with respect to t. And you get cosine of t. Right? If this is sine of theta, I want the derivative with respect to theta. That's just going to be cosine of theta. And so on, right? Okay? So we want to be clear, and remember, this is why I prefer this notation to just writing y prime, because these are all y prime, but in all three cases, the independent variable is different, right? Here it was x, here it was t, and here it was theta. So unless you write y prime of x or y prime of t or y prime of theta, then just writing y prime sort of obscures what the independent variable is. Okay. So again, I don't like the y prime, but within the context of the problem, it's okay. Just realize that it means three different things here in these three different cases. Okay. So I'm going to give you three examples here, right? The first one is to take the derivative of x cubed with respect to x. The second example is we're going to take the derivative of y cubed with respect to y. And in the third example, we're going to take the derivative of y cubed, but with respect to x. Okay. So yeah, up until now, we have not really emphasized what the independent variable is. I mean, it's usually explicit in the problem, but here it becomes very important because we get three different answers here. Okay, so the first one, I'm sure you can do this, right? You've done it many times. This is just 3x squared. So if I change everything to y, then I change the variable from x squared to y squared. So this is just 3y squared. Make sense? Now, what do we get in example 3 now? So if you're thinking, well, this is still just 3y squared, wait a minute. The independent variable here is x, not y. So you can't get the same thing, right? Oops, 3y squared. Yeah, what are we missing here? We don't know that y could be some function of x. Y might depend on x. And if that's the case, we have to apply the chain rule, right? We have to multiply by g prime of x. Or better yet, let's just leave it as the derivative of y with respect to x. Okay. So yeah, without the dy over dx, without this factor here, it's wrong. Because right, it looks like you get the same thing as in example 2, which was 3y squared. But notice, in that problem, the independent variable was y, not x. So one requires the chain rule, the other does not, right? And by the way, we can apply the chain rule to all of these. In the first example, well, I'm taking the derivative of x with respect to x. So by the chain rule, I would multiply by dx over dx. And in example 2, I would multiply by dy over dy. But the derivative of x with respect to x, right, is just 1. So if you forget the chain rule here, you're in luck because it's not necessary. You're just multiplying by 1. And the same thing is true here, right? This is just 3y squared times 1, or 3y squared. But in example 3, and this is crucial, these variables here don't match like they did in examples 1 and 2. And that's why we need the chain rule here, right? dy over dx is not equal to 1. Well, unless y is equal to x, right? But we don't know that. We don't know the explicit relationship between x and y here. It's not given. And if it's not given, then the derivative could be anything, right? It doesn't have to be 1. It could be 2 or 3, or it could be, cosine squared of 3x or something. It could be very complicated. Okay, so this is going to be very important going forward. Make sure you understand these 3 examples and why they're different. Okay, so now we can move on to implicit differentiation. And so there's really just 2 steps here. These are sort of the guidelines to finding the derivative implicitly. And that's what we're going to do here. So notice we have this equation here, right? It's x cubed minus 3xy squared plus 4y equals 12. And we want to find the derivative of y with respect to x. Okay? So what could we do? Well, one thing we could try to do is solve for y. Right? And if we can solve for y, we will have y as a function of x. And then we can just take the derivative, right? The usual way, explicitly. Okay. So, of course, you can solve this for y, but it's not going to be pleasant. After all, this is a quadratic equation in y. So you'll probably have to use the quadratic formula, which by now you should know pretty well. But that said, this is not the way to go, I think. Doing it this way doesn't make a lot of sense here. So we're going to do this implicitly, right? So the first step, as it says in the guide here, take the derivative of both sides with respect to the independent variable, in this case, with respect to x. Okay, so I'm going to take the derivative of the left side of the equation, and take the derivative of the right side of the equation. Right? So whatever you do to one side of the equation, you do to both sides. Right? As with anything. That's the golden rule of solving equations, right? Okay, so here we're taking the derivative, right? Now one side is completely trivial, right? The derivative of 12 is just 0. Right? 12 is a constant. That's, yeah. So the derivative of 12 is just 0. So this will all equal 0. So the hard part is the left side. The hard part is taking the derivative of the left side. And let's just go step by step here, right? This is a difference and a sum, so I can apply the sum rule, take the derivative of x cubed minus the derivative of 3xy squared plus the derivative of 4y. You'll notice I didn't need that much room here. I thought I was going to need some more space. All right, so that's a good first step, right? Just applying the sum rule and difference rule, same thing. We can also apply the constant times function rule. In other words, the 3 here can come in front, and the 4 can come in front. So let's do that on the next step here. Oh, well, yeah, what's the derivative of x cubed, right? 3x squared. That we can do in our heads, right? But these derivatives, hang on to these, right? All I'm going to do now is pull the 3 in front, and we still have to take the derivative of xy squared. Oops, squared. Right? Plus, and then bring the 4 in front, and then we have to take the derivative of y. And that's still all equal to 0. Okay, so far? All right. So the 3x squared is fine. In fact, we could subtract that from both sides, but let's do that later. We'll see in a minute. So this is 3. Now we need to take the derivative of xy squared. Okay, have you thought about that? Because I hope you don't get 2y. It's not 1 times 2y. Right? This is x times y squared. This is a product. You need the product rule, right? So in fact, I think I need more space here. So product rule is first times the derivative of the second plus the second times the derivative of the first. And then this is really just the derivative, 4 times the derivative of y. I can write that as 4 times the derivative of y with respect to x, right? All right, so the next stage here is really just take the derivative of y squared, which is not 2y, right? It's with respect to x, so we need the chain rule. The derivative of y with respect to x. Right. Plus y squared times, well, the derivative of x with respect to x, that's just 1. So y squared times 1, or just y squared, right? Plus 4 times the derivative of y. Still equal to 0. Okay, so far. Right? The rest is just algebra, right? We did all the calculus. We took all the derivatives. Now we just have to simplify this as best as we can. I'll leave the 3x squared for now. Should we distribute the negative 3 here? So this is going to be negative 3 times 2xy, so that's negative 6xy times the derivative of y. And then negative 3 times y squared is negative 3y squared. And then 4 times the derivative of y, nothing to do there, right? And that's supposed to be a y. So what are we trying to do here, right? Remember, we want to find the derivative. We want to find dy over dx, right? So, yep, we want to find dy over dx. We want to find this or this, right? And notice there's 2 of them, but that's what happens when you solve an equation, right? So keep in mind now, there's actually 3 variables here, right? There's 3 variables in this equation. What are they? Obviously, there's x, right? There's also a y. And then the third variable is the derivative of y. We're treating that as a separate variable. Right? Some people like writing y prime. I'm not going to do that, though. I'm going to leave it as dy over dx. Right? So that's the variable we're solving for. We're solving for dy over dx. which means anything that doesn't contain a dy over dx, we can subtract from both sides. We can subtract the 3x squared, and we can do, well, the opposite of subtracting 3y squared is adding 3y squared. So now on the left we have, let's see, negative 6xy times the derivative of y plus 4 times the derivative of y equals, well, negative 3x squared plus 3y squared. I was going to write it the other way, but that's fine. You can always change the order. Right. So this is what we're solving for. Notice it's a common factor in both these terms here, so we can factor out the dy over dx. When you factor it out, what does this multiply? It multiplies the negative 6xy plus the 4 here, and that's still equal to negative 3x squared plus 3y squared. Let's try that. Okay. And now we're really almost done here, right? We're solving for this variable here. Notice it multiplies all of this, 4 minus 6xy. So the opposite of multiplying by negative 6xy plus 4 is dividing by negative 6xy plus 4. But if you do that on the left side, you got to do it on the right side as well. Okay. Yeah, because on the left side, they cancel, right? You just get 1 times dy over dx. And there it is. So this is just negative 3x squared plus 3y squared divided by negative 6xy plus 4. And I don't see what else we can do. Of course, there's many ways we could write this. I would pull the positives in front. I would write this as 3y squared minus 3x squared over 4 minus 6xy. You know, that's the optimist in me. I like the positives in front. Right. So this is fine. Obviously, you could also leave it like this too. Or if you want, you can factor out the 3 as well. And in the denominator, you can also factor out a 2. But nothing cancels, so there wasn't much point in doing that. But, you know, if you like factoring, and you know, you could do it that way too. So, like I said, there's 3 different ways of writing. There's actually a lot more different ways you could write this. Any one of these is fine. There's no preference here. I mean, it doesn't look like this version is any simpler than this version, and this version is any simpler than this version. There's 3 different ways of writing it, so I'm fine with all 3. Okay, so that is the process of finding the derivative implicitly, right? We did this by implicit differentiation. Right. It's a fairly typical one, and you can see it's again, there's derivatives you have to take, and then there's also a lot of algebra. So at this point here, we already took all the derivatives. Now we're just solving for dy over dx, and that finds the derivative. So there might be something else that bothers you, right? Because usually when we take the derivative of something, you know, we might get something complicated, like, you know, 3 sine x over 4x squared plus 6x. I don't know, something like that. But up until now, we've never seen, you know, this derivative contain a factor of y. We've never seen, say, 4x squared plus 6xy, or the sine of x times y, right? We've never seen that till now, because it's always been a function of just x, right? Well, here, these, right, the derivative of y now depends both on x and y. And so that's a bit of a drawback, is that we can't rewrite this in terms of just x. We're going to have to deal with x and y on the right side of the derivative. Okay, so yeah, a slight drawback, but it's fine, right? And the idea is, if you want to find the slope of the tangent line, instead of saying find the slope of the tangent line at x equals 4, they would say find the slope of the tangent line at, at the point, 4, -7. So they would give you both the x and the y. And when you plug those numbers in, you just get a number, the slope of the tangent line. Or the instantaneous rate of change, right? It could be the velocity or something, right? So I hope that helps. And I'll do another example. And I'll actually do an easier one just to show you the idea of this. Okay, so next example, we want to find the slope of the tangent line to the graph of x squared plus y squared equals 100 at the point -6, 8. And if you watched the review video for test 1, you saw me do this one. This was actually on practice test 1. So what is it doing here? Well, if you remember, the idea was that the graph was a circle. So the graph looked like this. Again, the radius is 10. And at a given point on the graph, say this point right here, we want to find I think we wanted to find the equation of this line. In this case, we just want the slope. Right? And the way we did it was we used a trick. We used the fact that if we're passing through the center here, the radial line is perpendicular to the tangent line. And we can find the slope of the radial line because we have the center and this point. We have 2 points, so that's enough to find the slope of this line. And then to find the slope of the tangent line, well, we took the opposite reciprocal of this, right? So that's for perpendicular lines. Well, okay, but we had to use that trick, right? Suppose we didn't know that, right? Suppose we didn't know anything about radial lines and tangent lines are perpendicular to that, right? So here we're going to actually use calculus to do this, right? And here's how we're going to do it. How do you find the slope of the tangent line? Well, we need the derivative. We need dy over dx. So how can we do that with this equation? Just take the derivative of both sides, right? Implicitly. So take the derivative of x squared plus y squared on the left, and then take the derivative of 100 on the right. Okay, again, the right side is easy. The derivative of 100 is 0. Now, that may not always happen, right? We'll try to do another example where you don't get 0 on the right. But the point is, when it's an equation, you can always, subtract everything from one side and leaving you with 0 on the right, or with just a number on the right in this case. Right, so the left side's a little trickier, right? So this is the sum rule. We take the derivative of x squared plus the derivative of y squared. And that's still equal to 0. The derivative of x squared is 2x. And the derivative of y squared is 2y. And that's still equal to 0. Well, what do we do now? So remember, we want to find the slope of the tangent line. The slope of the tangent line, the only way to do that, other than to use this trick here that we did in chapter 1, is to find the derivative. Well, where's the derivative? I don't see any. So I deliberately made this mistake, hoping that you would catch it. Notice that we're taking the derivative of y squared with respect to x. What did I forget? I forgot the chain rule here. We have to multiply by the derivative of y with respect to x. Right? Because this is y, this is x. 2 different variables, right? Why didn't I do that with the derivative of x squared? Well, I could have, right? The chain rule says I multiplied by the derivative of x with respect to x. But that's just 1, so it's not necessary there. But it's absolutely crucial in the second term. Because, right, this is the variable we're solving for. So you can see what happens if you forget the chain rule, then you're stuck. You're not going to be able to find the derivative of y because you left it out. Okay, But now we can solve this for the derivative of y, right? Subtract the 2x from both sides. Oops. That's going to equal negative 2x. And now just divide by the 2y. Right? So over here, the 2's cancel, the y's cancel, everything cancels. Oh, and on the right, the 2's cancel as well. So what we're left with here is that the derivative of y is just equal to negative x over y. Okay. So that's the derivative, and that's the slope of the tangent line. At what point, though, right? We're looking at the point negative 6, 8. Right? So what's my m? My m is going to be the derivative after I plug in x equals negative 6 and y equals 8. So let's do that, right? This x is negative 6 and y is positive 8. Right. But keep in mind there's this negative in front here. So it's a negative of a negative, which is positive. And so this reduces to positive 3 over 4. Okay, so that's my slope, right? That's the slope of the tangent line. At that point. At a different point, of course, you'll get a different slope and so on, but that's right. So that's all we wanted to do here, right? If you want the equation, of course, well, you have the slope and you have your point, your x0, y0. That's still negative 6, 8. Now you just use the point slope formula that we've used many times already, right? So you just plug in these numbers here, and then you solve for y. And if I remember right, I think you just get y equals 3/4 times x plus 25 over 2. Because I think that's 12.5. That's the y-intercept. So it's the same answer we got on practice test 1 by using this trick up here that I'm erasing because it's not necessary now. Now we know how to take derivatives implicitly. Okay, so the answer here, the slope is just 3/4. And the equation of the tangent line is this. Okay, so I'm going to do this a slightly different way now. Right? So originally we had x squared plus y squared equals 100. And we found that the derivative of y with respect to x was negative x divided by y. Right? And we did that implicitly here, right? Okay. Right. It turns out, though, there's another way to do this, right? I can solve for y here. Right? Maybe not great, but I can solve for y. So if I subtract x squared from both sides, I get y squared is equal to 100 minus x squared. Okay, so far? Now, just take the square root of both sides. And y is going to be the square root of 100 minus x squared. But I'm forgetting something. What am I forgetting? Whenever you take the square root of both sides, right? Both sides, there's a plus and a minus. There's a positive square root and a negative square root, right? And again, this is just the equation of a circle, right? Remember, this was originally a circle. So what happens if you forget the minus sign? Then you don't get the circle. You don't get the full circle. What you get is, I'm trying to pick a color here, you get the top half of the circle, right? So that's the positive square root of 100 minus x squared. Right? And then the negative square root corresponds to the bottom half of the circle. That's the negative square root of 100 minus x squared. But if you want the full circle, you need both the positive and the negative. And of course, right, it's not a function, right? Because it fails the vertical line test. You have a vertical line crossing the graph more than once. Yep, that's not a function. Okay. However, remember the original problem. We want to find the slope of the tangent line at a specific point. That point being negative 6, 8, which is somewhere around here. So that should be the point negative 6, 8. So here's the x-axis, here's the y-axis, right? So notice where this point is. It's on the top half of the circle, right? Which means we can ignore the bottom half. We don't need the negative square root. So if you forgot the negative, then sure enough, you lucked out because we don't need it here. Okay. So now what do we do? Well, remember, we're looking for the derivative. We're looking for the slope of the tangent line. So now we just take the derivative of y the usual way. I'll rewrite this with the power 1/2. So now we take the derivative explicitly, just as we did in the last section. Of course, we do need the chain rule here, right? So this will be 1/2 times 100 minus x squared to the power negative 1/2, and then multiply by the derivative of what's inside the parentheses. In this case, 0 minus 2x, or just negative 2x. And I'm running out of space here. Let me see if I can squeeze that in here. So, so I'll pull the negative 2x in front, minus x squared to the negative 1/2, right? And 1/2 of negative 2x is just negative x. Oh, yeah, okay, I'll do that first. And then if you want to write this as a radical, the negative 1/2, when the exponent is negative, right, that means reciprocal, so it's in the denominator. And the exponent of 1/2 means it's the square root. Okay. So this is another way to write the derivative. And in fact, you'll notice that it's equivalent. What is the square root of 100 minus x squared? Well, that's just y. So in the end, this is just negative x over y. Right? And you can see it's the same answer we got by using implicit differentiation. Now, the only difference is that here, y could be positive or negative. Here, y has to be positive because it's the positive square root. But again, in our example, y is positive 8. So no harm, no foul there. It's the same thing. Okay, so the rest would be doing it the same way, right? So in this case, you can take the derivative explicitly if you ignore the fact that there's the negative square root here. So when you can solve for y, you can do it that way, right? Now, I don't think this was any easier than this. We got to the same answer, and in fact, I think this might be a little bit easier than this way, but that's just me. So now you have your choice. You can do implicit or explicit differentiation. In the first example here, though, I don't think we had a choice because solving for y, I don't think we were going to be able to do that. Not, without using the quadratic formula, that would not be an easy problem to do. And so going forward, most of the equations you're going to do this for will not be solvable for y. This being the exception, this being one where we could solve for y first, and we did that here, right? We solved this for y, and then we took the derivative the usual explicit way. Okay. All right, so let's do another one. We'll do this implicitly now. So I'll have to erase all this. Okay. So find the derivative of y with respect to x, right? For sine of 3x plus 4y equals x squared y. Okay. So this is one I can promise you will not be able to solve for y. Right? To be fair, I couldn't even do that, right? I could not solve for y explicitly in terms of x, right? Oh, you can take the arc sine of both sides, but you're going to have y on both sides still. Okay, so this is one that I don't think there's an easy way to solve for y, if at all. I certainly don't know how to do it. So in this case, we really don't have a choice. If we want to find the derivative, right, then we have to do it implicitly by taking the derivative of both sides. So take the derivative of the left side, and then the derivative of the right side. Okay. Now, right, remember I warned you earlier that up until now, the derivative of the right side was 0 because this was just a number. Well, now it's not a number. Now it's a function of both x and y. Okay. On the other hand, we could have subtracted x squared y from both sides and gotten that this equals 0. But you'll see it really doesn't matter. We didn't have to do it that way. So let's start on the left side, right? The derivative of sine is cosine. And this is not sine of x, it's the sine of a function. Well, actually, it's an equation or an expression with x and y. So we need the chain rule, multiplied by the derivative of what's inside the parentheses, right? So, yep, so we can leave the cosine of 3x minus 4y alone, and then the derivative of 3x minus 4y is 3 minus 4 times the derivative of y, right? The derivative of x is 1, but the derivative of y is the derivative of y. Okay. And I think that's it. I'll leave it like that. Remember, you're not taking the cosine of 3 minus 4 times the derivative of y. You're only taking the cosine of the 3x minus 4y. All right, so now let's go to the right side and let's take the derivative of x squared times y. So it's not 2x times, well, the derivative of y, right? Because this is a product. We need the product rule. First times the derivative of the second, plus second times the derivative, not the derivative of x, but the derivative of x squared. And I know we can do that in our heads, right? But let's do it on the next step. So we still have x squared times the derivative of y plus y times 2x, right? The derivative of x squared is just 2x. So I'll write that as 2xy. Okay. So far, so good. Right. So remember what we're solving for here. We're solving for the derivative of y, this variable here, in terms of x and y, right? So this is kind of a mess, right? I can subtract this from both sides. Maybe let's do that now. Right, so minus x squared times the derivative of y, and all of that is equal to just 2xy. On the right. So we'll leave that on the right. Yeah, but here's the issue, right? We can't divide by cosine of 3x minus 4y because it's not a factor of both, right? The parentheses, there's no parentheses here, right? So here's what I would do at this point. I would distribute the cosine to each term here. And this is going to be kind of a mess, but I think it's necessary. Well, maybe it's not necessary, but it's the way I would do it. So 3 cosine of 3x minus 4y, and then minus 4 times the cosine of 3x minus 4y times the derivative of y, and then minus x squared times the derivative of y. And that's still equal to 2xy. Okay. All right, so that's a little better because now this term here does not have a derivative with it, right? So this is something we can subtract from both sides. Okay. And on the left side, we still have, they're both negative, but I'm going to factor out the dy over dx. So this is our common factor here. Oops, sorry. I need to cross it out. This is our common factor. Let's factor it out. And it multiplies, we can factor out a negative as well. Multiplies 4 times the cosine of 3x minus 4y plus x squared. See, I factored out the negative sign, right? And this is still equal to 2xy, but now minus 3 times the cosine of 3x minus 4y. Right. And now we're almost done, because now I can divide by everything that's not the derivative, right? This whole factor here. 4 cosine of 3x minus 4y plus x squared. So on both sides. So on the left side, they cancel. And we're left with, oh, don't forget the negative. Negative dy by dx is equal to all of this. So I'm going to have to write it all over again. My bad. 4y all over this. Same thing. Phew. All right. So a lot of writing. But now we have to divide by the negative, right? Or multiply by -1. So multiply by -1 on the left and on the right. And so now we have finally the derivative of y with respect to x. It's just equal to all of this. And if it's all the same to you, I'm going to distribute the negative on the top. You can do it on the bottom too, by the way. But I think it'll look better on the top. So this will be positive 3 cosine of 3x minus 4y. That's a 4. And then minus 2xy. And then all divided by, so yep, the denominator stays. This is going to be 4 times the cosine of 3x minus 4y plus x squared. Okay, and that's it. That's the derivative. Yeah, again, a lot of algebra and a lot of derivatives as well. And don't forget the product rule. Don't forget the chain rule. Okay, you got to get used to those. And in doing all these problems, I'm hoping that you're getting that out of your system if you're forgetting the chain rule or you're forgetting the product rule, because it is easy to forget. I'll admit that much, but you got to get used to it, right? So for those of you, I hope you're not thinking, oh, can't I just cancel the cosines here? No, you can't do that. No, no, no. That's not going to work, right? Because they're not factors. These are not factors in the numerator and denominator, right? It's a factor of the 3 here and the 4, but it's not a factor of all of the minus 2xy and the x squared. Okay? So again, I know most of you knew that. I hope you knew that. But it's the same idea as this. If I have x plus 3 divided by x plus 2, you know that you don't cancel the x's, right? That's an algebra mistake. And I know we've all made that. I know I've made that mistake before, many times. But then you just have to learn when you can cancel and when you can't cancel. And here we cannot. So as messy as this is about as simple as it gets. I don't think there's any way we can simplify any further. Okay. So that's how this works, right? And again, I did one where the right side was just as bad as the left side, I think. But when you pull everything over, eventually you should be able to solve for the derivative of y. And that's what we wanted here, right? Find the derivative of y. Okay, I think I'll do one more, and I think I'll make it a hard one. How's that? And so I'm going to have to start all over again. Okay, so this is the hard one I was just talking about. We want to find the points on the circle. And I drew a little graph here. This is the circle of radius 5, right? So this is x squared plus y squared is equal to 25, which is 5 squared, right? So the radius is 5. And it's centered at the origin, right? The center is just 0, 0. And we want to find the points on the circle where the tangent lines pass through 0, 10. Okay, so 0, 10 is way up here, right? There's the point 0, 10, It's on the y-axis. It's you know, right? Now, if this looks weird to you, it's because this point is not on the circle, right? Up until now, well, we did this earlier, right? Find the equation of the tangent line to the circle at a point that's on the circle, like this, right? But this point is not on the circle. So how could there be a tangent line passing through this point? Well, there's a tangent line that touches the circle, but also passes through this point. Somewhere around here, right? If I draw the line, the tangent line at that point, it will also pass through the point 0, 10. Right. Likewise, there's another point, again, somewhere over here. If I draw the tangent line at that point, it will also cross at 0, 10. So there's two of them, right? There's one point over here and one point over here. We need to find both those points. Okay? So yeah, a point is an x and a y, so we have to find both the x and the y, right? And so how do we do that, right? So how do we find the slope of the tangent line? The slope of the tangent line is just the derivative, and then you plug in the x and the y. Right? So first we have to find the derivative. And we did that already, right? Remember, we did this implicitly, and we did it explicitly. The only difference is, the only difference is that the radius is different. In the previous problem, the radius was 10, right, because it equals 100. Here, the radius is 5. But either way, the derivative of 25 or the derivative of 100 is still 0. Okay. So again, you solve for the derivative of y, and you get negative x over y. Okay, so that's my slope, that's my m, at x and y. But notice, we don't know where x and y are. That's kind of the whole point, right? We're looking for these points. So it's not like we have numbers that we can plug in to the derivative here. So that's interesting, right? On the other hand, what else do we know about these lines here, right? They're tangent lines, right? So to find the slope, we need this here, right? But notice, if you consider this point here to be my x1, y1, we also know it contains this point here. We can think of that as my, x2, y2. I know I'm writing very small here, but I'm running out of space. So I can find the slope of this blue line here in two different ways. I can find the slope by just using the usual formula for slope, rise over run. Okay, so y2 is 10, y1 is just y, x2 is 0, and x1 is just x. So this will be 10 minus y over negative x, or I would prefer y minus 10 over positive x. Right, just bring the negative upstairs. Right. Okay, so this is another way to write the slope of this blue line, and it's also the slope of the tangent line. So it's also this, negative x over y. So these are both m, right? These are both equal to m. So these two things have to be equal. Right? So that is going to help us out a lot. If we set them equal to each other, we might be able to make some progress here, right? Let's just make sure I got this right. Negative x over y, right? Not negative y over x. Yeah. Yep, okay. Just making sure. And this is the difference in the y's over the difference in the x's. Okay. So how do we solve this? Well, we could cross multiply here. So if I multiply both sides by y, I get y times y minus 10. If I multiply both sides by x, I get negative x squared. And what does that give us? This gives us y squared minus 10y is equal to negative x squared. This is not what I was expecting, but I guess that's true. Right? So we get an equation with both x and y. So how do we solve for x? How do we solve for y? Yeah, I don't know either. I'm stumped. Yeah, again, it's the idea is we want to find both x and y. I was hoping that we would maybe eliminate the x or the y here, but I don't see that. Well, oh, okay, I got it. Going back and forth here really helps. I know I'm making you dizzy here. But look at the question and look at this equation. You see it? So here's the key. Right. This has to be true too, right? Because the point is on the circle. Well, here we go, right? If x squared plus y squared is equal to 25, then this had better be equal to 25. See that? So we can replace x squared plus y squared with 25 anywhere we see it because it's on the circle. Right? So this is just going to be 25 minus 10y equals 0. And now we can find y, right? Divide by negative 10. Y is going to be 25 over 10. Or if you prefer, 2.5 or 5 over 2. I would prefer one of these. Again, you do want to reduce your fractions here, right? So there you go. That does it, right? That tells us what y is. So yeah, it turns out to be exactly halfway up the circle here, right? Because if this is 5 up here, then this is 2.5, not 25, but 2.5, right? And it's the same for both, right? And you can see what's going to happen here with the x's. You're going to get the opposite x's. One will be positive, one will be negative, right? So there you go, right? Y is just 5 over 2 or 2.5. Now how do we find x? Well, it's on the circle, right? So replace y with 5 over 2. Don't forget you have to square it. And then solve for x. So 5 squared is 25. 2 squared is 4. And then subtract the 25 over 4 from each side. So minus 25 over 4, minus 25 over 4. And that's going to give us x squared plus 0 equals 75 over 4, right? 100 minus 25 is 75 over 4. And then take the square root of both sides. Do it vertically here. I have space. And I erase the 4. Yep, so x is going to be, don't forget the plus or minus, the square root of 75 over the square root of 4. Of course, the square root of 4 is 2. And this is going to be the square root of 25 times the square root of 3 over the square root of 4. So this will be 5 square root of 3 over 2. Right. Why do we get the plus or minus? Well, look at the circle here, right? You have 2 points, one with a one with a negative x, and then this one with a positive x. Right? So in fact, it's right there in the question. The question says find the points. There's two of them. Well, I mean, there could be 3 or 4 or 5, right? It's implying that there's more than one point, and there are. There's 2. Okay, so the points are, just to answer the question here, the points are negative 5 square root of 3 over 2, and then y is 5 over 2. Sorry, 5 over 2. And then the other one is with the positive 5 square root of 3 over 2, and then 5 over 2. Okay, so yeah, these are the 2 points on the circle whose tangent lines at those 2 points will intersect the point 0, 10. And that was the question. Find the points. We got them both. Okay, so yeah, kind of a tricky one. And in fact, I almost lost it here. This x squared plus y squared is the same as this x squared plus y squared. And if x squared plus y squared is equal to 25, then I can change this x squared plus y squared to 25, leaving the negative 10y, of course. And that's, So, look, there might be another way to do this. This is the way that, I sort of settled on here. But, if you find another way to do it, great. Yeah, we had to use the fact that it's the tangent line, but also the fact that it passes through 2 points, the point xy, which we didn't know, and the point 0, 10, which was given to us, right? The 0, 10 was given. And then, take the derivative to get the slope of the tangent line, and then find the slope of the line passing through 2 points using the usual definition of slope here. And then eventually, after you make these substitutions, you'll be able to find both y and x. And again, there's 2 points on the graph here. Although I probably shouldn't call it these because we use that for something else. But okay, so again, that was a slightly harder one, but and I think there's one like this maybe in the homework. And I don't think it's a circle there. I think it's an ellipse, actually. But, you know what an ellipse is, right? It's just an elongated circle. And the equation is a little bit different, but it's the same idea. So try that one in the homework. If you get stumped on it, again, refer to this, and this might help you out here. So I hope that helps. And that's implicit differentiation and some application of that too.